Last section we talked about the addition rules for probability, and we talked about the probability of, for example, wearing a blue shirt or a red shirt. They would be mutually exclusive. We talked about the idea of probability of eating steak for dinner or having mashed potatoes for dinner. Well, since both of those can happen at the same time, they'd be non-exclusive. Well, now we're going to look at the multiplication rules. And what if we're dealing with compound events? And how are we going to use those rules to find the probability of events occurring after one another? Well, the first thing we have to look at is if the two events are independent or dependent. If two events are independent, it means that one happening does not affect the likelihood of the other one happening. So in this case, the official definition, the fact that A does not affect the probability of B occurring. First example, flipping a coin, flipping a second coin, rolling a die. Two things that have nothing to do with each other. Well, if I flipped a coin and then I rolled a die, the fact that I got heads on the flip does not affect whether I'm going to get 1 through 6 on the die. So they would be independent events. If you're looking for the probability of two independent events, all you're simply going to do is multiply two probabilities together. We don't have to take into account how B is affected by A because these are independent of one another. Whether A occurs or doesn't occur, B is not affected. So let's look at an example. A coin is flipped and then a dice is rolled. Find the probability of getting a head on the coin and then a 6 on the die. Since these are independent, I just simply want to find the probability of a head, which we know is 1/2. The probability of a 6, which we know is 1 out of 6. So the probability of both things happening is a 1 out of 2, 1 out of 12. So if 12 things happen, in theory, one time I should get a head and then a 6 behind it. We talked about theoretical and experimental. This is what should happen in theory. Another example. A card is drawn from a deck. It's then put back into the deck and a second card is drawn. What's the probability of drawing a queen and a club? Since the card was replaced, these are independent events. The fact that the queen was drawn does not affect whether the club was pulled. Whether it's the queen of clubs or not, it is not affected. Please don't think of mutually exclusive and non-exclusive here. They have nothing to do with the multiplication rules. So then in this case, there's 4 out of 52 queens, 13 out of 52 are clubs. I'd multiply them together, and I'd simplify my answer. There's a 1 out of 52 chance that I will get a queen, put it back in the deck, and then I will get a club. It says nothing about the queen of clubs. Just a queen first, any of the 4 queens, followed by any of the 13 clubs. Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say they suffer from great stress. These are independent, because whether I suffer from stress or somebody in California suffers from stress, they have nothing to do with one another. So all I would do is find the probability of stress for the first person, probability of stress for the second person, probability of stress for the third person. Since they're independent, I'm just going to multiply them all together. We know that each one of them has a 0.46, 46%. So the probability that I'm going to find 3 people, all of which in a row say that they have stress at least once a week, is 0.097, which is about 10%. What if 2 events are dependent? So what if B is affected by whether A has happened or not? I got to change what's happening here a little bit. So if I draw a card from the deck, but I don't replace it, well, the first time there was 52 cards in the deck. Once I don't replace it, there's only 51 cards in the deck. So the probability of me drawing a particular card has decreased, has changed. Being a lifeguard and getting a suntan. Having high grades and getting a scholarship. These things are all related to each other. So the event of getting an ace on the first draw and a king on the second draw, but that first card was kept out. So the probability that I'm going to get an ace on the first draw is 4 out of 52. There's still 4 kings in the deck, but now there's only 51 cards. So the probability of me getting a king is 4 out of 51 this time. So now when I go through and I multiply, I end up with a 4 out of 363 chance. So there's 363 scenarios which could occur. 4 of them will give me an ace followed by a king. This is what we call conditional probability. The probability of getting a king given that an ace was already pulled. So that brings us to what conditional probability actually is. The conditional probability of event B in a relationship to event A is the probability that B occurs after A has already occurred. It doesn't talk about if A doesn't occur, only when A has occurred. The notation, and that's actually read as the probability of B happening given that A has happened. So the probability of B given A. That bar in between, given. And that's going to lead us to our second rule. Very similar here, except if you look at the back end, now we have a condition. The probability that A will occur times the probability that B will occur given that A has already occurred. If you think about this with the cards, the fact that probability of A was 4 out of 52, and then the probability of pulling a king given that an ace has been removed, that's where the 4 out of 51 came from. So here's our example. A person owns a collection of 30 CDs. 5 of them are the yes CDs. They want to select 2 at random. They're not going to put the CD back in. So what we're going to have to look at here is, what's the probability that they pull out a yes CD first? They don't replace that CD. So now there's only 29 CDs in the batch. Only 4 of them would be good here. Only 4 of them are yes CDs. So there's 5 out of 30 chance. The second time getting another CD that they want is 4 out of 29. So there's a 20 out of 870 or a 2 out of 87 chance. You want to make it a decimal, that's fine. But there's a very small chance that if I have 30 CDs that I will pick a yes CD, put it in the CD changer, and then pick another yes CD to put out. 3 cards are pulled from a deck and not replaced. The probability of pulling 3 jacks, well, in this case I know that there's 4 jacks in the deck, so it'd be 4 out of 52. Well, now there's only 51 cards in the deck. 3 of them are jacks, so 3 out of 51. Now there's only 50 cards in the deck. 2 of those are jacks. Multiply across. So if I pulled 3 cards out and didn't replace them, there's 5,525 different scenarios that could occur. One of those would give me 3 jacks. Which, if you think about a hand of poker, that's why getting 3 of a kind is a difficult thing to do. Getting an ace, getting a king, getting a queen. Not worried about the suit here. 4 out of 52 for aces. There's still 4 kings, so it's 4 out of 51 in this case because the card's been removed and ace has been removed. And then 4 out of 50 for the last card for the queen because there's already been 2 cards removed, 1 ace and 1 king. Remember, if that first pull is not an ace, none of this applies because we need an ace to happen and then a king and then a queen. If the ace isn't pulled first, we don't worry about anything else. Third example. For a local university, the probability that a freshman will have a car on campus is 0.2. The probability that a freshman will get a parking ticket over the course of the semester, given that he has a car on campus. We're not worried about the students that don't have the car on campus, only those that do. So the probability of C is equal to 0.2. The probability of getting a ticket given having the car, T given C, is 0.55. We just multiply those 2 numbers together. So the probability that a student will have a car and get a parking ticket in a semester is 0.11. We're not worried about the students that don't have a car. We're not worried about the students who have a car and don't get a ticket. These are just those students, 11 out of 100, would have a car and get a ticket over the course of the semester. When we talk about multiplication rules, you have to ask yourself right away, is the second event, dependent on the first event? If it is, that's conditional probability. You need to take that into account when you go ahead and find the probability of an event.